A couple of theorems that come in handy when we're working with our polynomials. First one is the remainder theorem, because at the end of the day that polynomial division, yeah, it's great, but it's time consuming and we can find information in quicker ways. So this theorem helps us. If all we're interested in is the remainder, then simply we just substitute a in, and then we know what the remainder will be when we divide by x minus a. A little proof of that. So there's our algorithm. Now, if we're saying the divisor is x minus a, polynomial x now becomes x minus a qx plus rx. If I substitute a in, then x minus a becomes a minus a. That goes away. And polynomial a equals remainder a. But we know that the remainder must be of degree 1 because we're dividing by a linear factor. And we said the degree of the remainder is less than the degree of the divisor. Therefore, the only possibility is it's of degree 0, it's a constant. So remainder a is the same as remainder x, because if it's a constant, it's not going to change. It's always going to be that value. So rx is a constant. So rx and ra are the same, therefore it must be polynomial a. There's our remainder. Now using that, here's the same question we looked at yesterday. Let's just show it. Gives the same answer. Substitute in 2 and sure enough, negative 19. Heck of a lot quicker than going through the whole of the polynomial division. But that then brings up an even better thing, the factor theorem. Because of course, if it is a factor, we know it has no remainder. So if I'm looking for factors, I just got to substitute the possibilities in. If I get an answer of 0, I know it's a factor. So we want to show x minus 2 is a factor of this polynomial and then go and factorise the whole thing. Okay, well, polynomial 2, yes, it turns out to be 0. So that confirms, yeah, x minus 2 is a factor. Hence factorise. Now here's the silly way of doing it. Oh, well now I'll go and do a polynomial division to work out what the other factor is. And so, alright, we go through our process. And the reason I say this is the silly way of doing it is, well, what was the point of using the factor theorem if in the end of the day I ended up doing a whole division and got 0 anyway? Oh, well, let's actually do this, and then I'll show you the sensible way of doing it. Alright, the other factor is x squared plus 2x minus 15, which then factorises to be x plus 5, x minus 3. This is the sensible way of doing it. And we just basically use logic. We say, well look, I know this whole thing's going to expand out, but what I do know is the leading term times the leading term must give me the leading term. Now x times whatever that leading term is must give me x cubed, so that must be x squared. But then the same deal with the constant. The constant times whatever that constant is should give me 30. Therefore, that's negative 15. Now the question is, well, what goes in the middle? Well, if I was to expand that out now, how many x's would I have? Well, I'd have minus 15x. Well, how many do I need? I need minus 19x. What's missing? How do I get from what I've got to what I need? Well, there's minus 4x is missing. Well, therefore, minus 4x, what's that? Minus 2 times the missing term. So the missing term is 2x. Got it done without doing the division. And then obviously we go and factorise like we did before. Okay, well let's try this one then. 4x cubed minus 16x squared minus 9x plus 36. We want to factorise that one. It is a cubic, so I know there is a linear factor. Because all polynomials can be broken down to be a mixture of quadratics and linear factors. So if it's of odd order, it must have a linear factor. Well, I know the constant factors in my expansion must go into the actual constant. So the numbers I'm looking for here are numbers that go into 36. Okay, there's a lot of possibilities I could try here. 1, 2, 3, 4, 6, 9, 12, 18 and 36. And of course, they could be negative numbers as well, so double that. But this polynomial is not monic. Now, any fractional factor, so if the answer was a half or something like that, would be in the form factors of the constant over factors of the leading coefficient. Which means every one of those possibilities could be over 4. Some of them we've already got, of course, because 4 over 4 is 1, and 12 over 4 is 3, and 36 over 4 is 9, but all of these other ones may be possibilities. And 2 is also a factor of 4, so I could put them all over 2. But again, we've repeated up some there, we can cancel some out. But I am left with all those possibilities, and of course they could be negative as well. So which one do we pick? Well, we pick sensible ones. The most logical, sensible one and easiest to substitute in is, of course, the number
1.
That's right, 4. No, it is of course 1. But look, 4 works. Oh, that was lucky, hey. So we tried 4, it works. We now know x minus 4 is a factor. Okay, now I can do the rest of it via logic. Leading term times leading term, that's got to be 4x squared. Constant times constant, that's got to be negative 9. How many x's do I have at this stage? Negative 9x, beautiful, that's what I want. Job done. That must be the factorisation. If you don't believe me, you could try it with the x squareds as well and say, well, what have I got at this stage? Well, minus 4 times 4x squared, that is minus 16x squared, yeah. Okay. But of course, 4x squared minus 9 factorises, and we get x minus 4, 2x plus 3, 2x minus 3. Very old HSC question. So they've given us a polynomial, x plus 1, x minus 3 times some quotient, plus, and they've written the remainder in a strange way, a outside of x plus 1 plus b. We're told that when it is divided by x plus 1, the remainder is negative 11, but when it's divided by x minus 3, the remainder is 1. What is b? It's just a matter of using our factor theorem or our remainder theorem depending on the situation. In this case, we've got a remainder. So when I substitute in negative 1, I get negative 11. Negative 1's nice, of course, because all of these things become 0, and straight away I'm just left with b as negative 11. Now, the second part. Well, what would the remainder be when we actually do that division of x plus 1, x minus 3? Well, the other bit of information I haven't used is polynomial 3 is equal to 1. Substitute that in, and the first bit disappears, and I've got 4a plus b is equal to 1. So I now know a is equal to 3 because we've already worked out b is negative 11. Now our remainder, it was written in a strange form, but there it is, ax plus 1 plus b. I do now know what a and b are, so the remainder must have been 3x minus 8. So there's our answer. Try this one. Suppose x cubed minus 2x squared plus a is the same as x plus 2 times some quotient plus 3. Simply asking us, find the value of a. Well, polynomial negative 2 is equal to 3, because that's effectively what we're saying here. When I divide by x plus 2, I get a remainder of 3. That's what that's saying. If I work with the left-hand side, then sub in negative 2, we're saying, well, this should be 3. And then we just get a is 19. Wow, now we're really going back in time, 1994. When the polynomial px is divided by, this time it's divided by a quadratic, the quotient is qx, the remainder is rx. Y is the most general form of the remainder given by this. So an explanation. And all they're really looking for is that idea, well, the degree of the remainder should be less than the degree of the divisor. I'm dividing by a quadratic, therefore the degree at the most could be 1. I mean, it might not be, it might be a constant. But it could be a linear function. So ax plus b would be an expression for the remainder. As I say, a might equal 0, but it's still in that form. Given that polynomial 4 is negative 5, show that remainder 4 is negative 5. Well, let's substitute in. 4 minus 4 is 0, that goes away. So polynomial 4 does equal remainder 4. So yeah, remainder 4 is negative 5. Further. When we divide by x plus 1, the remainder is 5. Now go and find what the remainder is. So we know remainder 4 is equal to negative 5. That's what we just worked out. So if I put that into our ax plus b, I know 4a plus b is negative 5. The other piece of information they've just given me, when I sub in negative 1, I get 5. Minus a plus b is equal to 5. Simultaneous equations now. We get a is negative 2, subbing back in, b is 3, so our remainder is minus 2x plus 3. Okay, so 10d, I've just made a little note there, is if the factor is 2x minus 1, you've got to ask yourself what would make it equal to 0. That's basically what you're substituting in. So a half would make that equal to 0, so that's what I would test with the factor theorem.